So far we've been looking at what a vector field is, and in particular learning about conservative vector fields. There are two operations that we're going to learn to use on vector fields that are sort of operations that we wouldn't recognize from previous algebra. One is called the divergence, and it's a rather simple calculation in terms of how to do the calculation. In terms of what it's used for, that's quite a bit deeper. And I've got resources for my own students. If you're not in my class, I highly recommend just searching what is the divergence of a vector field. And there are so many sources out there for you to look at. So, given a vector field, in this case that has two components, and remember, each component can have variables x and y in them. So these are functions or scalar functions. The divergence of that vector field is a calculation that just simply says what is the x partial derivative of m, or the partial derivative with respect to x. Oops, that should be a comma. That's the worst comma ever. Plus the partial derivative of the y component with respect to y. And algebraically, you add these two together and you're going to get yourself a scalar value. Let me just put a little note here. It's no longer a vector. Not a vector. The calculation of this is going to be pretty straightforward because we've been doing lots of partial derivatives. But let me just show you there's an alternate notation for this. Some texts use the gradient symbol, dot product the vector field to look at this calculation. And the way you would interpret that is, what if you had a vector that said we're going to take the partial derivative with respect to x and the partial derivative with respect to y, dot product the vector field m comma n, and they're making it look almost as if you're multiplying these two together, but you're not. And the same thing is you're multiplying these two together. Anyway, this is the calculation at the end. There are many sources talking about how this and this are not necessarily bad choices for notation. I'm doing this as a warning to my students because textbooks love shorthand, and shortcuts are only really good if you understand them. Now, for an example, if we have this vector field, y squared plus sine of xy, comma, x cubed y plus e to the y power, the divergence of this vector field is going to be the x partial derivative of these components would be 0 plus cosine of xy multiplied by, that's right, times y, plus, now we need to do the partial with respect to y. That will be x cubed plus e to the y. And if there were like terms, I would combine them together. But I think I'll just close this example by writing it as the sum of three terms. I highly encourage you to look at sort of the deeper meanings of what is divergence in terms of its physics application. It's particularly interesting if you look at it in terms of fluid flow, but it gets used in electricity and magnetism and other places. One more quick thing before I close this out. If our vector had 3 components, the divergence of that vector field would be each term's appropriate or matching partial derivative. So m with respect to x plus n with respect to y plus p with respect to z. Now we're not going to be using these calculations for a little while in our textbook. The author just loves to introduce all the foundation material now, and we'll need this tool a little bit later on. So I'll let you guys find an example suitable for testing out a 3-variable case. It's not that difficult. Until next time.